Hello everyone, I am Rishma Adesha. We are here to present our IPD topic Performance Analysis of Hybrid Quantum Classical Convolutional Neural Networks for Audio Classification on behalf of my team, which consists of Bhuvi Ghosh, Yash Thakur, and myself. This is the agenda for today's presentation. Our study aims to tackle the challenges of audio data classification using a novel hybrid approach combining classical and quantum neural networks. As we know, audio signals are inherently complex and multidimensional, containing attributes like frequency content, amplitude variations, and temporal patterns. These intricate characteristics make it challenging for conventional machine learning techniques to achieve effective classification. Traditional methods for classifying audio data include techniques like MFCC, linear predictive coding, and spectrogram analysis. While these methods convert audio signals into numerical or visual representations, they often struggle to capture and model the intricate patterns and relationships present in the data. To address these challenges, this study proposes the use of MEL spectrograms, which provide a visual encoding of the audio signal's frequency content over time. Convolutional neural networks, or CNNs, are particularly well suited for analyzing these MEL spectrograms as they can effectively identify intricate spatial patterns and features within visual representations. However, as the volume variations and dimensionality of audio data continue to increase, classical computational techniques face limitations in terms of processing power, memory requirements, and classification accuracy. This is where the potential of quantum computing comes into play. The study investigates a hybrid quantum convolutional neural network or QCNN model consisting of a CNN for feature extraction from MEL spectrogram representations of audio signals and a quantum neural network layer for classification. The CNN excels at capturing spatial patterns and hierarchical features, making it well suited for extracting relevant audio features. The QNN layer leverages quantum computing principles to classify the audio data based on the extracted features, potentially offering advantages over classical neural networks for complex, high dimensional data. By combining CNNs for feature extraction and QNNs for classification, the study aims to develop an efficient framework for audio classification that can handle the complexities and increasing scale of audio data.
Coming to the literature survey, we've divided the papers in two categories, the first being classical ML and the second being quantum machine learning. Classical machine learning dealt with two kinds of inputs. First is the numeric representation of audio data that is obtained using MFCC, MEL frequency substrate coefficients, and the second being spectrograms, that are the visual representations of audio data. When it came to spectrograms, the authors have used CNNs and ANNs for classifying MEL spectrograms. CNNs achieved an accuracy of 81.75%, while ANNs achieved an accuracy of 94%. The authors who have dealt with the numeric data obtained from MFCC have achieved an accuracy of 70.58% for classifying COVID 19 cough samples. There were further advanced techniques that have been used to classify audio data that involve transfer learning and ensembling, especially using ResNet 50 architecture, whose output is ensembled with the SVM predictions, attaining an accuracy of 91.10%. There were architectures involving transformers and conformers, which involved audio spin transformer that had a shifted window scheme for efficient self-attention computation, and conformer models that combined convolutions along with transformers to achieve state-of-the-art performance on audio classification tasks. Now moving on to quantum machine learning. Quantum machine learning, we dealt with three types of approaches. One was quantum convolution neural network, the second being hybrid quantum classical convolution neural network, and the third being quantum neural networks. For quantum convolution neural networks, they leveraged quantum CNNs for feature extraction as well as classifications both, getting an accuracy of 93%, which surpassed the accuracy of 85% of the classical model. In hybrid quantum classical neural networks, the authors have used Earth observed data for classifying images in the field of remote sensing. Their models surpass the classical model. In quantum neural networks, they proposed a deep quantum neural network for classifying cancer based on endoscopic images, achieving an accuracy of 0.948, which surpassed its classical counterparts. There was also a quantum support vector classifier that was used to classify cardiovascular diseases. It implemented a quantum architecture which achieved an accuracy of 97.31, again surpassing its classical counterpart.
The gaps that we found in the literature survey include quantum machine learning shows potential in image classification, but its application in audio classification is limited. There is a lack of research on utilizing quantum circuits in conjunction with CNNs for audio classification. The gap in the literature survey highlights an opportunity to innovate by combining quantum techniques with CNNs for enhanced audio classification performance.
Coming to the problem definition and objective of our project, we aim to investigate the use of a hybrid QCCNN, that is, a hybrid quantum classical convolutional neural network architecture for classifying high dimensional audio data using spectrogram representations of audio data. We also aim to expand the scope of our study by using two types of dataset: the smaller GTs and music classification dataset containing 100 audio samples per class, and the larger birdsong dataset containing 1,000 audio samples per class. We further aim to evaluate our model based on metrics including accuracy, precision, recall, F1 score, and binary cross entropy loss.
To evaluate the hybrid quantum classical CNN thoroughly, we have created a system architecture to build and evaluate the neural networks. It highlights the critical steps involved, including data preparation, feature extraction, which was done using MEL spectrograms, and the models that we have used, the training of the classical CNN and the quantum classical CNN models. It measures the prediction performance and evaluation using relevant metrics such as accuracy, precision, recall, F1 score, and binary cross entropy loss of the models. For the datasets, we have used the GTs and music genre dataset, which consists of 100 audio files per genre. And for the larger dataset, we have used the birdsong dataset, which consists of 1,000 audio files per bird species. The CNN architecture, as shown, consists of three convolution layers followed by match pooling layers and fully connected layers at the end for classification. The convolution layers help systematically apply learnable filters to the input data and extract spatial hierarchies of the features. The convolution layers have a ReLU activation function, which introduces nonlinearity in the model. The match pooling layers are interspersed between the convolution layers, which serve to downsample the feature maps, and a 2D dropout layer is incorporated that helps for generalization ability of the model. The model uses stochastic gradient descent with momentum as the optimization algorithm. SGD iteratively updates the network parameters based on gradients of the loss function. The loss function used is the binary cross entropy loss, both of which can be mathematically shown with equations on the screen. The binary cross entropy loss is employed as the optimization criterion because of its ability to quantify the output based on the prediction confidence. Furthermore, we have shown the architecture of the QCCNN model. The classical part of the model is the convolutional neural network, which comprises of three convolutional layers followed by ReLU activation function and interspersed with max pooling layers and a dropout layer. The CNN component extracts high-level features from the input data through convolution operations. The output from the second fully connected layer of the CNN model is passed to an estimator QNN layer. This is the quantum part of the QCCNN model. The estimator QNN is a parameterized quantum circuit with 8 qubits, which composes of a feature map and the ANSAT circuit, which can be shown with the mathematical equation on the screen. The estimator QNN takes in this quantum circuit QC as the input, and the input parameters from feature map will be treated as network input and weight parameters. The quantum feature map basically converts classical data to quantum data through a parameterized quantum circuit. The ZZ feature map being used in the quantum circuit QC is a second order poly Z evolution circuit. The ZZ feature map embedding for n-dimensional classical data on n qubits can be shown with the equation on the screen. The real amplitude circuit NSATs being used in the proposed architecture has one repetition on 8 qubits with full entanglement.
Coming to the analysis of results, the results demonstrated that the hybrid quantum classical convolutional neural network architecture attained a reduction in overfitting on the larger dataset as compared to its classical counterpart, yielding a significant increase in test accuracy. A notable observation was the positive correlation between overall accuracy and dataset size. As the volume of the training data increased, the hybrid architecture exhibited a corresponding rise in the overall accuracy of classification. Concurrently, the hybrid approach demonstrated a substantial reduction in overfitting when compared to its performance on the smaller dataset. An elevated cross entropy loss implied a higher degree of uncertainty in the predicted probability for individual instances in case of the GTs and music genre classification dataset. This uncertainty was further reduced when the large size bird song dataset was used. The high cross entropy loss and good accuracy suggested that the proposed hybrid model is performing well in terms of overall classification accuracy but is struggling with confidence or precision in its probability estimates for each specific data point.
So far, this study investigates the use of MEL spectrograms for audio classification using a hybrid quantum classical convolutional neural network architecture, which helps to classify the intricate audio data. The proposed model consists of a classical CNN, which was integrated with a quantum neural network layer and was evaluated on two distinct datasets of varying sizes. The QCCNN model achieved a training accuracy of 0.9875, which was comparable to its classical counterpart for the smaller GTZAN dataset. However, it struggled on generalization on the test data. For the larger dataset of birdsong, it surpassed its classical counterpart with a testing accuracy of 0.9504 as compared to 0.9288 of classical CNN model, and it also mitigated the issue of overfitting. There was also a significant decrease in cross entropy loss of the proposed hybrid model with an increase in the number of iterations when tested on the larger birdsong dataset, thereby underscoring the importance of increase in data for achieving better generalization. This study highlights and backs up potential advantages offered by QCCNN architectures in handling high dimensional and complex audio data. For the future scope of this work, there is a lack of explainability and interpretability in QML models because of their complex nature. Future work could focus on developing quantum specific explainability techniques to provide insights into decision making process of the QCCNNs. Future work in terms of audio classification could also focus on utilizing a pure quantum neural network architecture rather than a hybrid QCCNN architecture to analyze its efficiency in terms of computation, speed, and generalization on real world data. Thank you.